8 patients, different severities. Who gets treated first? Scan every card. Compare. The sickest patient is severity 8, treated, gone. But now, a new patient arrives. Severity 9, critical. Who's next? You scanned everyone. Again, every single 1, 10 patients, 100, 1,000. Every time someone new arrives, you start from scratch. That's not triage. That's a system failing. Every lookup costs n. Do it n times. That's n squared. For 1,000 patients, that's 1,000,000 scans. What if the sickest patient was always at the top? No scanning, no searching, just there. This is a heap, and today we're going to build one from scratch. This is a complete binary tree. Every level is completely filled, left to right. No gaps, and it has one rule. Every parent is greater than or equal to its children, not just the root. Every parent, every level. That's the heap property. A tree with this property is called a max heap, and the root is always the maximum. Now notice something. 7 is on the left, 8 is on the right. 8 is bigger, so shouldn't it be on the left? No. The heap doesn't care about left versus right, it only cares about parent versus child. 7 and 8 can be in any order. The heap is not sorted, and that's completely fine. But where does this tree actually live? In memory? Right here, in a flat array. Read level by level, the root goes to index 0, its children go to 1 and 2. Their children, 3, 4, 5, 6. And the last level, 7 and 8, and so on. Every node has a home in the array, and here's the beautiful part. To find any node's left child, 2i plus 1, right child, 2i plus 2. Parent, I minus 1, divided by 2. Let's try it. Node at index 1, 2 times 1 plus 1 is 3. Left child is 4, 2 times 1 plus 2 is 4. Right child is 5. Same connections. No pointers, no linked list. The array is the tree. But what if a node is in the wrong spot? What if a small value ends up at the top? Compare with both children. 9 is the biggest. Swap. Again, compare. 5 is bigger. Swap. And now, 2 has no more children. It stops. This process is called Heapify. The node sinks to where it belongs, and it takes at most log-n steps, because the tree is only log-n levels deep. So how do we build a heap from a random, unsorted array? Start at the bottom. Heapify the lowest parents first, then work your way up. 4 calls, bottom to top, and the whole array becomes a max heap. And here's the surprise. Building the heap is only O of n, not O of n log n. We'll prove why later, and that's why the sickest patient is always at the top. No scanning, the heap just knows. Alright, we know what a heap is. We know Heapify sinks a node. We know build heap works bottom to top. Let's write it down. Heapify takes 3 things: the array, the size of the heap, and the index of the node we're fixing. We start by assuming the parent is the largest. Then we find its children, using the formulas we learned. If the left child exists, and it's bigger than our current largest, then the left child is the new largest. Same check for the right child. So after these 2 checks, largest points to whoever is biggest, the parent, the left child, or the right child. And here's the key. If the largest isn't the parent, we swap them, and then we call Heapify again on the position where the parent just sank to. That's the recursion. The node keeps sinking until it finds its place, or hits a leaf, and it takes at most log-n steps. The height of the tree. Build the whole heap, just one loop. We get the size, and we start at the last parent, n over 2 minus 1, and walk backwards to the root. Why start there? Because every leaf is already a valid heap. No children to violate. So we skip the entire bottom half. At each step, we call Heapify. Fix that node, move up. Fix the next, and remember from last time, this whole loop is just O of n. The math is surprising, but it works. Here's the full picture. Heap sort. Phase 1, build the max heap. 1 call. After this, the maximum is guaranteed to be at index 0. The root is the champion. Phase 2. This is where the sorting actually happens. We loop from the end of the array back to 1. Each round we swap the max, R0, with the last unsorted element. The max is now locked in its final position. Done forever. But now the root is wrong. Whatever we swapped up isn't the max. So we heapify the root, but notice we pass I, not n. The heap just got one element smaller. The locked element at the end is no longer part of the heap, and we repeat. Swap the max to the end, shrink the heap, heapify, swap, shrink, heapify. 3 procedures. Heapify is the engine. Build heap assembles the structure, and heap sort drives the whole thing. That's the complete algorithm, on paper, but reading it and seeing it are two very different things. We've got the algorithm on paper, 3 procedures. Now let's watch it work. Here's our input. 8 numbers, completely unsorted, and here's the same data. As a tree. Remember, the array is the tree. Phase 1. Build the max heap. We start at the last parent, index 3, and work backwards. Index 3, value 1. Its left child is at index 7. Value 4. 4 is bigger than 1. No right child, so 4 is the largest. Swap. 1 is now a leaf. No more children. Done. Index 2, value 3. Left child is 7. Right child is 2. 7 wins. Swap. 3 is now a leaf. Done. Index 1, value 5. 8 is the largest child. Swap. 5 lands at a leaf. No recursion needed. And finally, the root. Index 0, value 6. 8 is bigger. Swap. 8 rises to the top, but we're not done. 6 just moved down. We need to check it. Its children are 4 and 5. 6 is still bigger than both. No swap. The recursion stops, and there it is. A valid max heap. 8 at the root, the maximum. Every parent is bigger than its children. Phase 2. The sorting loop. Each round, take the max, lock it at the end, and restore the heap. The max is 8. The last unsorted element is 1. Swap them. 8 is now in its final position, locked, done forever. But now the root is 1, way too small. Heapify. 1 sinks, past 7, past 3, all the way down. The heap is restored. 7 is the new champion. Swap 7 to the end, lock it. Heapify. 2 sinks past 6, past 5. New champion 6, swap, lock. Heapify. Same pattern every time. Swap, lock, heapify. Swap, lock, heapify. Swap, lock, heapify. Last swap. 1, 2, 3, 4, 5, 6, 7, 8. That's heap sort. Build the heap, then extract the max, over and over. The heap does the heavy lifting. Next, let's write the real code. Now let's write the real Python code. We'll start with the core engine, Heapify. This is the function that sinks a misplaced node down to where it belongs. Def Heapify. It takes the array, the heap size n, and the index I of the node we want to fix. We start by assuming the parent at index I is the largest. Then we check if we're wrong. Left child, the formula we learned. 2 times I plus 1. Right child, 2 times I plus 2. First, does the left child even exist? If it does, and it's bigger than our current largest, then the left child takes the crown. Same check for the right child. Does it exist? Is it bigger than our current largest? If so, right child becomes the new champion. Now the key question, did the parent lose? If largest isn't I anymore, the heap property is broken. Swap them. The bigger value rises up, and recurse, the value we push down might still be too small for its new subtree. Keep sinking until it settles. That's the entire engine. Compare 3 values. Swap if the parent lost. Recurse. Now let's use this engine to sort. Def heap parchage sort takes just the array. Everything happens in place. Grab the length. We'll need it for the heap boundary. Phase 1. Build the max heap. Start from the last non-leaf, n over 2 minus 1, and work backwards to the root. Call Heapify at each position, bottom up. The whole array becomes a valid max heap. Phase 2. Extract the maximum, 1 by 1. We loop from the last index down to 1. Swap the root, which is always the current max, with the last unsorted element. The max is now locked in its final position. Heapify the root again. Notice I, not n. The heap shrinks by 1 each round. 2 functions. That's all of heap sort. Let's test it on our familiar array. The same 8 numbers from the dry run. Save and run. Building the heap first. There's our max heap. Now extracting, each round the heap shrinks. And there it is. Clean, efficient, in place. Let's start with build heap. How fast is it really? Imagine the heap as a tower. The ground floor has about half our elements, the leaves. They do 0 work, 0 swaps. They're free. 1 floor up, about a quarter of the elements. Each one does at most 1 swap. 1 coin per worker. Next floor, 1/8 of the elements. 2 swaps each. And at the very top, 1 lonely CEO. Log n swaps, the most work of anyone. But look at the pattern. Most of the workers are on the bottom floors. They barely sweat. The expensive workers, there's almost none of them. The math works out beautifully. Each floor's total cost is bounded. The whole sum converges to just about 2n. Building the entire heap is just O of n linear. Most students assume O of n log n. But when most of your workers are free, the total payroll is surprisingly cheap. Now the full picture. What's the total time? After building the heap, we extract the max n times. Each extraction needs a heapify. That's log n work. Watch. Again and again. N champions. Log n rounds each. And here's what makes Heap Sort special. This is the same for best, average, and worst case. No degenerate inputs. Ever. What about memory? This is where Heap Sort really shines. All 3 start with the same array. Now watch what happens during sorting. Heap Sort works entirely in place. No extra memory at all. But merge sort, it needs a copy of the array for every merge. And quick sort stacks up recursive call frames. O of 1, O of n, O of log n. Heap Sort wins. But Heap Sort has one weakness. Is it stable? During extraction, the root swaps with the last element. That's a long-distance jump. And that jump can scramble the order of equal values. After the swap, B comes before A. The original order? Broken. Long-distance swaps have no way to preserve relative order. So how does Heap Sort stack up against its rivals? Heap Sort, the reliable guardian. Guaranteed O of n log n, 0 extra memory. Quick Sort, the speed demon. Fast in practice, but vulnerable to that quadratic worst case. Merge Sort, the stable strategist. Always in log n, preserves order but eats memory. Each has its place. Choose Heap Sort when you need guaranteed performance with 0 extra memory.